Hello, everyone. Welcome to another episode of the Blaspheming Bite. Today, we are shaking things up a little bit. We are not even going to attempt to do a problem. We are just going to look at some basics of trees. Now, trees are very important for interviews. If you don't know trees, you don't know graphs, and if you don't know graphs, you can't get into the top engineering companies. That's just the basic. Graphs are everywhere, trees are everywhere, and if you didn't follow my sequence of questions for recursion, you might want to go back and get a good grasp of recursion, because every tree question invariably boils down to a recursion problem. Without recursion, there is no trees, and it doesn't work the other way though. You can have recursion questions which do not involve trees, but trees and recursion, yeah, go hand in hand. You cannot have trees without recursion. All that time wasted talking about trees and recursion, let's actually start talking about what a tree is. Specifically, we are going to be dealing with something called the binary tree. Called a binary tree. Now, let's look at this example of a tree that I have painstakingly created over here, which is an exact replica of the example that Elements of Programming Interviews has given me. I was so shameless, I did not even try to change the sequence of nodes. I did not even change the values inside the node, so good job, me. So some basic definitions. Now, the first guy here, it's called A. This is the root of the tree. And if you notice, there is nothing about the root. Now, this is a very philosophical question, and it's a religious question also. So you know that people say that everything in the world needs a creator, but then who created the creator? So in this question, this tree, if I'm starting off at M, I know that somebody came before me, and somebody came before him, and somebody came before him, and him, and him, and then all the way up to A. So A is God, but where did A come from? We're not going to go into that. It is just created. It's just bits, the zeros and ones. It's there. So that guy there is called it's called a root. Okay, that's a root, not Groot. It's a root. And then everyone that comes below a root is a child. Now for this example, A, what are the children of A? It's B and I, right? So that's called a root. Now I told you earlier that we're going to be looking at binary trees. What do you mean by a binary tree? So binary tree is if you've got a node. Maybe I should have defined node before. So a node is everything you see here. A is a node, I is a node, O is a node, O is a node, P is a node. All of these are nodes, right? Now every node will have a maximum of 2 children. That's what basically a binary tree. So you cannot have 3, like, so you can't draw something like, does it have 3? Okay, let's say that he points to Z with a value of -225. So right now he's got 3 children, and that's just not right. We have to follow some protocols, right? We can't just do whatever we want to do. Moving on. If we center ourselves at A, what is this part called? That part is called the left subtree, and this part is called the right subtree. Not really that important, but it's something that you can remember. Moving on, if you've noticed that every node has a parent child, has a has a parent child. What the hell am I talking about? Has a parent, but the root node does not have a parent. That's the guard guard node. Let's call it the guard node. Another thing that you can talk about is, let's say you take a node, and let's say that you're taking node P. How do you get from node A to node P? So you would go to A to I to O to P, right? Now this is sometimes called the search path. So you might be asked a question: how many hops does it take to reach node P starting from the root? Really ugly questions are like, let's say you're given a node, and then you're supposed to find how many hops it takes to reach P, either going through the root or through some other path. So it could be like go like this and then go down, or it could be maybe there's a connection here, and then you could go like this. So a lot of different possibilities. That's just basically talking about what a search path is. Now we talked about this child and parent stuff. That's going to be coming up in a lot in all of our topics, because it's a very important thing. So another way of talking about a parent-child relationship is also an ancestor-descendant relationship. So if you take an example of K, how many ancestors does it have? It's got 3 ancestors. So J is an ancestor, J is an ancestor, I is an ancestor, A is an ancestor. Without doubt, you can say for every node other than the root node, you can for sure say that the root node is an ancestor, right? It's also something else interesting. Every node, by definition, is an ancestor and a descendant of itself. And that's something interesting to note, because that helps us define what a leaf node is. So in this example, you can see that the highlighted nodes are actually leaf nodes. And by using the ancestor descendant explanation or definition, you can define what a leaf node is. If your node does not have a descendant, and that's basically a leaf node, okay? A descendant except for itself, because we know that every node is by definition an ancestor and a descendant of itself. Moving on, there are some concepts that we have to know when we tackle these problems. The first one is something called depth of a node. So depth of a node is basically telling you how far beneath the root node are we. So if you take the example of A, how far beneath the root node are we? 0, because we are not beneath the root. But if you take I or B, then your depth is going to be 1, correct? Now let's go to M. So you've gone 1 level, 2, depth 2, depth up, depth 3, depth 4, finally depth 5. So if you want to look at M, the depth is actually 5. Okay. So that's a definition of depth. Another definition that you have to remember is that of a height of a tree. Now, in this example, what do you think the height of the tree is? Height of the tree can be defined as the depth of the highest depth of any of the nodes, right? And it'll always be a leaf, right? Because if it's not a leaf, then you can obviously go one more level, one more level down, right? So height of a tree, what is in this example? It's going to be 5. Now, what is a level? That's the last definition we're going to take before we stop this part of the video. I'll be back. Don't worry. I'll be back. So, what is a level? A level is nodes that are all at the same height. Okay, or depth. I mean, sorry, on the same depth. Height is of the tree, right? So, in this example, nodes H, L, and N, they're at the same level. All these are the same level. All these are the same level. All these are the same level. So that's basically the definition of the depth, height, and level of the tree. So we got some more interesting definitions that are coming up. Stay tuned.